Welcome to your lesson on continuous exponential growth and decay. So let's talk about compound interest to begin. This connects directly to the investigation you did last week on compound interest and what happens when you compound to infinity. So let's say you invest some money and the bank tells you that they will give you an 8% interest rate. This means that at the end of the year, you will get 8% on top of the money you invested. So whatever you put in, they give you 8% of that, and then your bank account or investment rises in value. That's called simple interest. However, compounding is what is more commonly done in investments or banking. Compounding is the number of times per year that the rate or interest rate is applied. For example, if the bank compounds monthly, so now instead of paying you once at the end of the year, then they will give you interest 12 times per year, but they won't give you that original 8% every time because that would be way too much money. Instead, they take you the 8% they offered you as their annual rate, they divide that by 12, and they give you 0.66% per month. So they pay you 12 times, but they divide the whole rate by 12 to give you just a portion every time. Still ends up being more money because you earn a little money, then the next month you earn money on your original money and the money that you earned for your first month's interest and so on. So you're earning on top of your original principal investment and also on the interest you've earned every time you're making interest on top of that. All right, so in your exploration, you also took the basic exponential growth model and adjusted that to create a model called the future value formula, or basically this is a formula used to find the value of an investment in the future. So that model is a basic exponential growth model. This model for finding future value of an investment is exactly the same. The only difference is that we take the rate divided by k, and up here we multiply by k. And that k, if you look here, is the number of compounding periods per year. So again, if you had an annual interest rate and it was applied every year, you would just use this model, right? It would be 1 plus whatever the interest rate is. If it was 5%, you would do 1 plus 0.05. And you put here the number of years. But if they're compounding, you have to divide the rate by, just like we did in the last example, by 12. Here we divide by some number, the number of compounds in the year. And here we multiply by that amount also, because if they're paying you 12 times a year, then if you do it for 2 years, you'll do the 12 payments per year times 2 years will give you 24 payments in total. So that's that formula used for that. All right, so in the investigation, you also looked at what happens when you take $10,000 and you invest it at 7% interest, compounded annually, once a year, monthly, daily, hourly, what happens? So again, we begin with our basic exponential growth model. We adjust it to create the future value model, and we see what happens. So if you have annual compounding, k is 1. So if this value is 1 and this value is 1, we just have that 1 plus 0.07, the 7%. And there's the 20 years that that's invested for. It gives you this amount. Now what happens when you compound monthly? Now k is 12. So now instead of 20 years, we still have 20 years, but each year is 12 payments. So 20 times 12 makes 240. But here we have to divide the rate by 12. So that annual rate of 7% is divided by 12 to give us that rate that they will pay us every month. So there's the formula. There's the amount it gives you. Notice it went up a little bit when the compounding went up. And here we compounded daily. We're using 360 for daily. This number went up again because it's k times 20 years times 360. And here we divide the rate into a daily rate. So 7% divided by 360 gives us a daily rate. And again, since we raised compounding, the amount we make went up. But it didn't go up as much. This one went up much more than this one. This one just went up a little bit. And finally, here's compounded hourly. There's this many hours in a year. Therefore, we take 20 years times this, and we get this many total payments in 20 years. That's a lot of payments. And for 1 year, we take the 7% divided by this many hours to get an hourly rate of interest. And it gives us this amount. Again, it went up, but very little this time, just a little bit. So it's going to go up every time, but go up less and less every time. So there's a limit to how much you can go up. All right, so again, what happens, you also looked at this, when you take $1, 100% interest, compounded infinitely. So we're going to take that model and go even further. Well, we did hourly last time, but what if you just went to infinity? What would happen? So here's annual, right? So there's a 1 plus, there's a 100% is 1, right? We don't have to put 0.0 anything anymore because it's 100% interest. So 1, we divide it by 1 because there's only one compound. It's going for 1 year. We make $2. So that makes sense. You have $1 You get 100% interest. That means you get $1 back. That means you have $2. That's your future value at the end of the year, $2. Now, if you semi-annually, means twice a year, you get compounds. So you take the 100% divided by 2, which will give you 0.5, which is 50%. That makes sense. That'll be 1.5. And here's 2 payments in the year. You get this amount. Keep going. Quarterly, monthly, weekly. There's 52 weeks in a year. So you do the 100% rate divided by 52. You get your new rate. And then 52 payments. You get this amount. Daily, 365. Hourly, 8760. Every minute, every second, that many seconds in a year. So watch what happens to your investment. Goes up to $2 and $2.25, $2.44. It's going up, going up, going up, but it's going up slower. Look, now it's going up really slowly, 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 and eventually it all ends up being almost pretty much the same number, 2.71828. It's basically approaching this limit. That number is your limit, so you cannot earn any more than that. Even if you did more compounds, it would go up slightly, but basically be evening out around 2.71. All right, that number is a special number because 2.71. 2.718 actually is E, this number E, which we called a very important number in math. It's the base of our natural log. So E is an important number. This reaches that limit, so that this must be an important number. And we know that it approaches that. But that was a very special investment. That investment was for exactly this part here when it was $1, 100%, 1 year, all those things were set. So basically when you had this part here for that $1, 1 year, 100% situation, all of that, when you made it infinite compounds, see k became infinity, and you put infinity here, this thing here, when those became infinity, that number approached E. So basically in this future value formula, all of this approached E when this was made infinity. So we put this here for infinite or continuous compounding. We made that whole base E because all of that became E basically. All right. So that leads to that. That leads to this formula. So that formula changes into this continuous or infinite compounding. This is E, and then we put R and T here. If you're curious how that R and T pops in there, well, that's what the last part of the investigation was all about. But basically, that's our rate of interest, and there's the number of years. Why RT? So if you're wondering about that, there's an algebraic and a calculus derivation of the formula provided on the next 2 slides. So if you are interested in that, just pause the video on the next slide and see if you can figure it out. Here's the algebraic proof. Why is it RT? This was the last page on your investigation. See if you understand what's going on there, but basically proves that you begin with this formula, our future value formula, and you get to this one for continuous compounding, and it shows the steps along the way. Now that's an algebraic approach to it, using basically laws of exponents and some fractions. But there's also the calculus approach. In the calculus approach, we use something called limits. Basically, it's explained here, and you can check this out as well if you're interested in that or have any background or interest in calculus. Check it out. All right, so that gives you a little bit on that. Make sure you now practice using this infinite compounding. It's not just used for investments or finance. It's used for any time anything is growing exponentially, but at a continuous rate. All right, so there's a couple problems here. Might want to pause it and try it with some teammates there. See if you can solve this problem. It basically tells you that there's continuous compounding going on or continuous growth, so you can use that A equals P ERT formula and see how you do. Next, when you press this video, press pause now because then the answer will be revealed in just a moment. So there's the answer. You can check your work and pause it if you need to look some more. And one more question. See if you can do this one. Again, pause here because the answer will appear in just a moment. So here's the answer to this one. Hope those made sense, using basically the idea of using E as a base when you have continuous growth happening. All right, great work. There's more practice where that came from. You can find it in the practice assignment listed in this or linked in this lesson. You can do it.